So as we're discussing these remainder and factor theorems, let me show you kind of a way to think about how this all connects. Let's say we have the equation or the function f of x equals x squared minus x minus 6. Okay? Well, we know from factoring, this is a quadratic, so we know it's going to make a parabola shape. And if we factor it, we would get x minus 3 and x plus 2. Okay? So the zeros of this function, so these are the two factors. The zeros of this function are positive 3 and negative 2. If x plus 2 is the factor, the zero is negative 2. If x minus 3 is a factor, then positive 3 is a zero. So notice what happens when I graph that. And it doesn't matter whether I put it in the original form or in the factor form, either way. Sure enough, it hits the x-axis at negative 2, which came from the factor x plus 2, and it hits the x-axis at positive 3, which came from the factor x minus 3. Okay? Now, notice, if 3 is a 0, x minus 3 is a factor, which means f of 3 should equal 0. If I put 3 in for x, 3 squared minus 3 minus 6. Sure enough, that does equal 0 because this graph remember, hit the x-axis at negative 2 and positive 3. This graph goes through the point 3, 0. When x is 3, y is 0. That's the point on the graph, okay? So there's an x-intercept of 3, 0, or the other one over here would be negative 2, 0. So notice how we get all that from the factor form, okay? So look what up here what they're telling us to try as another example here, okay? Divide f of x equals 2x to the third minus 7x squared minus 5x plus 4 by x plus 1. Now, we don't know why they picked x plus 1, okay, but they want us to divide by x plus 1. Well, one option is to do synthetic division. Put negative 1 in the box and see what we get as a remainder, okay? So, let's see here. Oops. Negative 1 times negative 9 is positive 9. Negative 5 and positive 9 is 4. And we get a remainder of 0. Okay, now we don't know why they picked x plus 1, but they told us to divide by x plus 1. Okay, so since the remainder was 0, by the way, I could have done this as well. I could have plugged negative 1 in for x. So 2 times negative 1 to the third minus 7 times negative 1 squared minus 5 times negative 1 plus 4. If I typed that in my calculator, I would have also gotten 0. Okay? All right. So what do I know about f of negative 1? F of negative 1 equals 0. Okay? So x plus 1 is a factor. So I could either do synthetic division and see that my remainder was 0, or I could plug in negative 1 for x and get 0 to know that the remainder is 0. But since the remainder is 0, that means that x plus 1 is a factor. So negative 1 is a 0. That means the graph will hit the x-axis at the point negative 1, 0. X plus 1 is the factor. In fact, I'm going to write that in another color. X plus 1 is a factor, which means negative 1 is a 0, which means the point negative 1, 0 is an x-intercept. See how all three of those statements are true and are connected. That's the big idea that we need to get out of this section in 3.3. Okay? All right, now notice our depressed polynomial. When we divided by negative 1, by x plus 1, by putting negative 1 in the box here, our depressed polynomial was 2x squared minus 9x plus 4. Okay? If I set that equal to 0, I could factor it. If you're not so good at factoring, you could do quadratic formula. But I think I can factor that. I think it's going to factor let's see, 2x and plus 1 and x minus 4, I think would be the factored form of that. And if these two things multiply to be 0, then either 2x plus 1 equals 0 or x minus 4 equals 0. If 2x plus 1 equals 0, I can subtract 1 from both sides, divide by 2 on both sides, and I get x equals negative half. If x minus 4 equals 0, then x equals positive 4. So notice what just happened. I found that negative 1 was a 0, but now I also know that negative 1/2 is a 0, and positive 4 is a 0. This graph, the original graph, this function right here, is going to hit the x-axis at the point negative 1, 0, which we already got a while ago. And now we know the other one is, or the other ones rather, are positive 1/2. I'm sorry. I missed a sign right here, didn't I? Those were both negative, weren't they? Hang on. Nope, they were both negative. Yep, they were both negative. Okay, so I should have said 2x. Go back right here. I should have said 2x minus 1 equals 0. So I add 1 to both sides. I messed up on my factoring there. I wasn't paying close enough attention. 2x equals 1, divide by 2. So x is 1/2. So it's positive 1/2, that's the 0, and positive 4. So my zeros are negative 1, positive 1/2, and 4. So my x-intercepts, where it hits the x-axis, is negative 1, 0, positive 1/2, 0, and positive 4, 0. Okay? If x minus 4 is a factor, then positive 4 is a 0. If 2x minus 1 is a factor, then positive 1/2 is a 0. And watch this right here. If I graph my original, here's my original function. And sure enough, the graph hits the x-axis at negative 1, 0. That was one of our x-intercepts, negative 1. Positive 4, 0. And then this one right here, it's kind of hard to tell. It's between 0 and 1. 1/2 seems like a reasonable number for it. It's kind of hard to tell just by looking at the graph, but once we think that's what it factored to, we can verify that. So notice this original polynomial, even though they gave it to us in regular form instead of factored form, we know that it would have factored to x plus 1 because we put negative 1 in the box and negative 1 was the 0, x minus 4, I know a factor is x minus 4 because that's what it factored to, and positive 4 was my 0, and 2x minus 1 because positive 1/2 down here was my 0, okay? So this is the factored form of what they gave us. We just needed a little hint to know that x plus 1 was something that we should try dividing by. In section 3.4, we're going to get better about knowing, hey, where did they come up with this x plus 1? Why did they suggest that we try that one for our synthetic division, okay? Okay, a little bit more on this idea here about zeros. Notice these parabolas right here. This particular equation was y equals x squared minus 1. Now notice that x squared minus 1 would factor to x plus 1, x minus 1. It's a difference of squares. Since x plus 1 is a factor, negative 1 is an x-intercept. Since x minus 1 is a factor, positive 1 is an x-intercept, is a 0. Okay? So our two zeros, the degree was 2 and we had two zeros. It was the opposite numbers from this factored form. Notice that this one right here, this x minus 1 squared, that means there's two sets of x minus 1. This has a multiplicity of 2. So the only 0 was positive 1, but it occurred twice. And we learned in 3.2 that if you have a multiplicity of 2, the graph will touch that point and then go back the same way it came. So it didn't cross. Oh, on this one, it crossed at negative 1 and positive 1 because their multiplicities were 1. It actually crossed through the x-axis and then went back up. This one, because the multiplicity is 2, it touches at positive 1, opposite value of those numbers in there, positive 1, but it's a multiplicity of 2, which means it touches and went back the way it came. Notice this one. This one does not touch the x-axis at all. And the equation for this one was x squared plus 1 equals 0. I can't factor it. It's not a difference of squares. If I tried to isolate the square root, I subtract 1 on both sides and take the square root, I get positive and negative I, because the square root of negative 1 is imaginary. Because those zeros are imaginary, this graph does not hit the x-axis. So if you ever have a parabola that doesn't touch the x-axis, it doesn't have any zeros, okay? They're not real numbers. They're imaginary numbers. And those imaginary numbers will come in pairs called conjugates. So as a recap, if r, some number r, 2, 7, negative 3, whatever, if r is a 0, then r is a solution to the equation. In other words, you set the function equal to 0, that number r would work. Which means x minus r is the factor, and the point r comma 0 is an x-intercept. It's where the graph hits the x-axis. Notice that if there is an imaginary 0, they come in pairs. You'll never have just one imaginary 0. It will be both, the positive I and the negative I. Okay? All right, so sometimes quadratics do not have real numbers for their x-intercepts. Okay? So they may not be real numbers, but they will be complex. In other words, they can have I in them. They can be imaginary. Every quadratic will have two solutions. They're either both real numbers or both imaginary numbers. Okay, so let's try this one. They want to know where this graph is going to hit the x-axis. So what we do is we say, okay, well, when will it equal 0? Remember, if you want to find the x-intercept, you put 0 for y. I'll just tell you this will not factor. We could try it, but it's not going to work. So we can't factor it. We go to the quadratic formula. X equals negative b plus or minus the square root, b squared minus 4ac, all over 2a. My a value is 1, because it's in front of x squared. My b value is 4, it's in front of the plane x. And my c value is 5. So I'm going to work this formula with those numbers plugged in. So negative b. b is 4, so negative b is negative 4, plus or minus the square root of b squared, so 4 squared, minus 4 times 1 times 5, all over 2a, and a is 1. Okay, I'm going to type in the part under the radical. So I'll have 4 squared minus 4 times 1 times 5, and that comes out to be negative 4. So under the radical, I should have a negative 4. X equals negative 4 plus or minus the square root of negative 4 divided by 2. Okay. Square root of negative 4 is an imaginary number. So I'm going to have x equals negative 4 plus or minus 2i, because the square root of 4 is 2, but I need an I on it because that will be an imaginary number, divided by 2. Notice the negative 4 is getting divided by 2, and the 2i is getting divided by 2. Negative 4 divided by 2 is negative 2. 2i divided by 2 is 1i, or I. So negative 2 plus or minus I. Okay? So the solutions to this quadratic, the zeros, the places that make this equation equal 0, one of them is negative 2 plus I, and the other one is negative 2 minus I. They are exactly the same, except for one has a plus before the I and the other has a minus before the I. We call those conjugates, or complex conjugates, meaning they're exactly the same except for the sign on the I. Okay? Notice if I graphed this, if I graphed y equals x squared plus 4x plus 5, this graph does not hit the x-axis. It gets close, but it doesn't touch the x-axis. The reason for that is the zeros were imaginary numbers. There are no real numbers that we could put in for x that would make this equation equal 0. Okay? So we have complex zeros. Notice, imaginary zeros always come in pairs. That's a theorem called our conjugate pairs theorem. Okay? So if a minus bi is one of your zeros, then the other one will be a plus bi. So exactly the same numbers, a and b, except one will have a plus, one will have a minus. Okay? So if I is one of your zeros, the other zero will be negative I. If negative 6i is a zero, the other one will be positive 6i. If negative 2 minus 4i is a zero, the other one will be negative 2 plus 4i. Okay? The real number part will keep the sign. It's the imaginary part that changes signs. So if 1 plus 3i is a zero, 1 minus 3i is the other one. Negative 7 minus I is the other one that's paired with this. And 5 minus 8i, the other zero would be 5 plus 8i. The real number keeps the sign. The imaginary part changes. Those will be the two zeros because imaginary numbers come in pairs when we're finding our zeros. Okay? All right.